So today we will have quite mathematically strongly lessons, maybe one of the most mathematically strongly. So if you have any problem, ask or ask to your colleagues. No, it won't be too much. I will try to be as low as possible. But by the way, since yesterday I was discussing with some of you concerning the exam, no? So the exam will be a written exam. And I think there will be a mixture of exercise and also theoretical question. So from my side, since we didn't do any kind of, we just analyzed theoretically how the GFD phenomena can be described mathematically speaking, okay? And actually, we can consider, for example, the Ekman layers as a sort of theory, but also as a practical example of how the geostrophic flow behaves when it's close to a boundary, okay? So, tomorrow I hope to have time to make a couple of exercises on the stratification, but taking account that the question will be mostly theoretical, okay? So, for example, explain how starting from the primitive equation we reach the theoretical, the geostrophic flow and describe the property of the geostrophic flow, okay? So let's take the primitive equation, I consider Rossby number much smaller than 1, temporal number much smaller than 1, homogeneous fluid, blah blah blah, no friction, and so I obtain this equation. This equation gives me, for example, that I do not have shear in the vertical, which is called the Taylor-Putman theorem, and in case of F-plane approximation, I can have perfect divergence in the horizontal, blah, 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 blah. Okay? So you can write as much as you want. Of course, there will be time, but it's important to, I wanted to just overline the fact that even if not always I did all the calculation between one, let's say, statement and the following, I expect that as a homework you will do it, okay? So I don't ask you, of course, because it's just time lost that you cover papers and papers of calculation demonstration, which is, but for your career, for your experience and your growth, I think that it's important that you become confident with the demonstration, with calculation, but most importantly in our case, with all that concern the scale analysis. So to say, okay, this is much smaller than this is much larger than this is dominant. So what are the dominant aspects that govern a specific geophysical flow, that dynamic flows, okay? So this is the idea. Okay, so yesterday we arrived to practically describe very easily, I would say, but I would say also quite specifically the Kelvin-Helmholtz systemability. Okay, so we understand the presence of a mixed zone, which can engulf the entire system if certain conditions are satisfied, or can be localized close to the interface, because as we have said yesterday, every system which is formed by two layers, stratified, is unconditionally unstable. Okay, so it's enough that we have a waves which is short enough to give rise to the instability and to create the Kelvin-Helmholtz instability. Okay, so today we want to make one step ahead more and try to ask what happens when we have a specific density stratification, which is n expressed by n squared. So when we have the stratification which is described by the dense by the gradient, vertical gradient of density perturbation, and we know that is expressed by the Bloom-Weisser frequency. So when we have this kind of density, which means that exists, of course, in this case linear, we can start with a very simple case of a linear stratification. So, what is the critical velocity shear? So, which is the velocity shear du dz? So, how much it should be with respect to n squared? Okay. This is interesting because we have seen that yesterday we analyzed the scale of the mixing length of the mixing layer, and we saw that actually that was derived from energetic consideration. Okay, so we saw the potential energy gain, the kinetic energy loss in the case of a very simple two-layer flow, and we found that there was a relationship between the two energies. So if the potential energy is enough strong, I can make a lot of, I need a lot of energy, kinetic energy, to overcome the stratification, to destroy the stratification. Otherwise, if my velocity shear is weak, I cannot hope to destroy the stratification, and I will maintain the, let's say, the very small, very short, narrow mixed layer. So now we want to understand something more, and to do like this, to reach the solution, which will be in any case not so exact as we expect, because otherwise this shouldn't be a course for, introductory course for GFD. So we can take a 2D plan, which has two dimensions, one in X and one in Z. So at the moment we neglect the Y, or we consider symmetry in the Y direction. We do not consider any kind of, this is correct. We do not consider any friction, okay? So, no friction, and also no rotation in this case. So the equation that we expect, starting from our equation, which are always the primitive equation, are this. So we have, of course, we do not have anything in Y, so the Y momentum equation can be neglected. We can neglect also the velocity in Y direction. So we obtain is the time derivative in U and W. Then we have the advection within the Y component. We do not have Coriolis. We maintain, of course, the pressure gradient and the buoyancy effect. We still have, of course, the continuity equation, again without V, and we have also the energy equation, which, as you remember, was turned into a density equation, again without the Y component. Okay, so these are our starting equation. So our starting equation, as you might see, we have a new term which we never considered so far, which is the local derivative of W, of the velocity, of the vertical velocity. Okay, but our idea is to have, so, like a stratified flow. So we have density here, let's say zeta1, and density here zeta2. And this will be smaller than density zeta1. Then we will have, for example, a certain uz. Okay? So, in particular, I will use the bar over the u in order to represent the fact that this is the driving force. Okay? So the shear, the vertical shear, is what actually can create instability or can avoid to create instability. It depends how will be. So I will use this. How will be the relationship between this one, which in some sense is related to the kinetic energy, to the transfer of kinetic energy, and the Brunner-Weiser frequency, which is related to stratification. So this is a problem then that can be solved by means of the perturbation theory. Why? Because we have a main flow, and then we suspect to have some waves which will have a velocity u prime and a velocity along u and a velocity along w prime, but we do not expect to have w bar different from zero. So we impose that the average vertical velocity is equal to zero. So in general, we can say that u, which is in general a function of x, z, and t, will be equal to u bar, which is a function only of z, plus a certain u prime, which is a function of the three variables. Then we will have w, which in general is again a w bar plus w prime x z t, but we impose that we do not have any average vertical velocity, okay? Because the flow is going in this direction. This is our hypothesis. We don't know to have mean vertical velocity, so to have like big waves, let's say, large scale waves, or something which is going in this direction. Also because u is constant in time, okay? It's a steady. So it's something, it's like in laboratory. In laboratory you impose a vertical shear like that one we saw. We watched yesterday from the video. Okay, then we have P, which, don't forget, this is the dynamic pressure, which will be P bar Z plus P prime X, Z, and T. And in particular, we can say that P bar Z, if we work a little bit with the equation, we will have that so that P bar is in hydrostatic balance with buoyancy. And finally, we have rho, which will be rho Z plus rho prime X Z. So we have, in some sense, decomposed the entire our system in a system which has a, let's say, steady component along the vertical, okay? Because the vertical is our, important dimension in this case, plus a series of perturbation in all the variables we are interested, which in the most general case depends on x, z, and t. Okay, let me just write this one. Well, good. when we analyzed the barotropic waves, you remember that we imposed, when we solved the Poincare waves, that our system, which was barotropic, without any kind of problems, I mean, in the density, could satisfy equation, wavy solution, sorry. Okay, so Fourier-like equations, Fourier-like solutions. So what we can do here is do the same. So we will have u bar z plus, so this u prime x z t will be something which will have okay, so the perturbation is further decomposed in a term which is dependent only on the x and the t, so the propagation, the dimension, and time, which is actually harmonic function, okay, sinus and cosinus, multiplied by the real unknown of the problem, which is the perturbation over the z. And I can do the same exactly with all the other. Okay, so if we start to transfer this expression of our unknown to the system, I will have that, for example, for the first term, I will have the t. So u will be u bar plus u prime. Okay, so I just substitute the value of u bar plus u prime, in the first term. Then I will have u bar plus u prime, the x, u bar plus u prime. Finally, I will have w prime, because I don't have anything, any average, or let's say basic, we can call it this part basic flow, and this is the perturbation. So w prime d z u bar plus u prime equal to minus 1 rho 0 p bar plus p prime x derivative. Okay, so is u bar dependent on t? No. Is u bar dependent on x? No. Is u bar dependent on z? Yes. Is p bar dependent on x? No. So I start to create some simplification. So what I obtain is du prime dt plus, now I have two terms, u bar du prime dx plus u prime du prime dx plus w prime. Now the partial derivative in u bar can become total derivative, because u bar is just a function of z, plus w prime du prime dz equal to 0 p prime dx. Okay, to this equation I make a further approximation. So as we did for the barotropic, for the analysis of the barotropic flow, I want to linearize my my system. What does it mean? It means that when I write something like this, I implicitly assume that I do not have any kind of further order terms, okay? So all the, let's say, all the perturbation is included, is described by these prime terms. This mostly means that all the terms which are at the second order must be removed. Which means that this term here, which is u prime, I can neglect. And this term here, which is w prime, u prime, can be neglected. Okay? So I obtain with du prime plus u bar du prime dx, w prime du bar dz, and the variation in x of the perturbation of pressure. Okay, so similar thing I can do for the equation in W, and what I obtain is d w prime dt. This is easy, it's just a substitution, plus there I have u bar for sure, u bar dw prime dx, but I can remove the second term, u prime the w prime dx, because it's second order. So I can go on, and here I only have w prime dw prime dz, so I can go on. Second part, so now I have minus 1 over rho 0 d dz p bar plus p prime minus rho bar plus rho prime g over rho 0. So you can see that this term here and this term here can be neglected because we have this expression here. So this and this can be removed. And so I obtain, oh no, sorry, it is not yet. And so, okay, but you'll see it later. And so I obtain just again the, let's say, in this part only, of course, if I wouldn't have W prime, I would have again the hydrostatic approximation. But in this case, the hydrostatic approximation is not satisfied because I still have something on the left-hand side which is a perturbation, okay, still. So it's like we are having a hydrostatic balance which is perturbed, okay? There is always this story in this course. I have a basic flow and I have a perturbation. Initially we started with the basic flow, then we we concluded the part of the rotation with the perturbation to the basic flow, which was practically a perturbation to the geostrophic flow in different aspects. Okay, so from the point of view of the planetary waves or the topographic waves, or looking more in detail to very subinertial waves. Okay, so see, yes.
Yes, why is it that the P bar is not dependent on Z?
No, P bar is dependent on Z, because when I extract this, I will have that the total derivative of P bar and rho bar multiplied by this. But I know that the total derivative of P bar is in hydrostatic balance with the basic density. That's why I can remove this and this, okay? So if you express this, you will have minus 1 rho 0 d P bar dz, because it's only dependent on Z, plus the P prime dz, and then I will have minus rho 0, minus rho bar g rho 0 minus rho prime g rho 0. And this term here is exactly equal to this one, and so I can remove it. Okay, continuity equation, pretty easy, because what I obtain is just can write it here. So I have a derivative in x of u, so I just act on du prime dx plus w prime dz. Finally, I have d rho dt, so this is just d rho prime dt, plus I have u bar d rho prime, because rho bar is just dependent on z, so u bar d rho prime dx, and then the u prime d rho prime can be neglected because it's second order, plus w prime, and here I just have d rho dz, because the term where I have d rho prime dz, okay, is neglected because I'm having a multiplication with the w prime, so it's a second order.
Excuse me, Professor. Just thinking out loud. In the first equation, on the right we have a term of 1 over rho naught d dx of p prime.
P bar plus p prime, yeah.
So, aren't we taking into consideration the scale analysis where probably I think the perturbation p naught is really, really very small in consideration with the rho naught which is dividing over it. Therefore, it will become really, really very, very small.
So you,
on the right.
so you are, this is pressure, You are considering this one or this one? Maybe this one with rho. So you are referring to the boosting approximation. So don't forget that this is always our perturbation density. Okay? So we cannot in any case neglect this with respect to this. Okay? What we are going to do is to remove, but not by neglection, by linearization, but just because there is the hydrostatic balance which govern this and this, okay, on the basic flow, okay. While here we are just making, we are not considering any kind of approximation, because what we obtain is just p prime, which is a function of x. That's why we can keep it. While p bar is a function just of z, and having here a derivative on x, of course it will be 0. Okay? Okay, so as the slide says, we can apply the basic state, the small perturbation. We then act with to linearize our equation. So the basic state consists steady, sheared, horizontal flow with u bar and w bar equal to 0 in a vertical density stratification. The accompanying pressure field P bar obeys to the hydrostatic balance, and then when we add a small perturbation, we have the linearization of the equation, which is practically what we obtain. Okay. Okay. So now we can start to solve our system, at least as much as we can. So the first thing that we can do is to solve the fourth equation. So the fourth equation is an equation in rho. So what we can do is to apply this expression here. So rho will be rho bar z plus exponential. And we also add a new term, which is called psi, and is called the string function. Which is related to the two velocity component, to the two perturbation velocity component. So we have that U prime will be dz psi, and W prime will be minus dx psi. This helps us because in some sense, we reduce two unknowns to just one. So psi is a function of x, z, and t in the most general case. And if we define the U prime and W prime in this way, you can see that we can satisfy the continuity equation, okay? Because we will have the first term, which is the mixed derivative xz of psi, which multiplies by the mixed derivative again of psi, but there is a minus, and so we satisfy the continuity equation. Okay, so the first term tells us that we want the time derivative of rho prime. So if we look to rho prime, the only place where we have time is here. So the time derivative will be practically minus ELC multiplied by rho prime, because this is 0. What we obtain is this one. Okay, so if we make the time derivative of this, we will obtain minus ILC multiplied by the rest of the term, which can be written again as rho prime.
So, how to spell?
Sorry?
I was confused until you mentioned it. Is it L or E? The I?
This is I, L, minus X minus CT. So this is the expression of a wave which has wavelength 2 pi over L, okay? So it is this wave here, which is traveling within, it's the perturbation actually, that we hypothesize, which is like this, like a typical Fourier-like wave, which is traveling within our system, okay? It's like could be, for example, the effect of the wind or any kind of trigger mechanism. Okay, second term, U bar, now we have the X derivative of rho prime. Okay, again, this is 0. The X derivative is IL and then rho prime again. Plus W prime multiplied by d rho bar dz. But d rho bar dz is exactly related to our Brun-Weisler frequency. So it will be minus rho 0 n squared g. And this is equal to 0. Rho prime, W prime is equal to minus dx psi. So we can also say that psi is equal to E again. So we still decompose also for psi in a wave-like behavior multiplied by the dependency of psi in the vertical. Okay? So when we do W prime, so since W prime is minus dx psi, minus dx psi, again we can say that is minus EL psi. So what we obtain is an equation which has rho prime and psi as unknown. And we can solve it for rho prime. We can put everything together, and we can also neglect the terms IL. So we will have that rho prime will be equal to minus n squared rho 0 over g u bar minus c multiplied by c. So there is a term which is practically a constant, I would say, with the exception of c, because c is the phase velocity, okay? So in principle, we don't know the phase velocity, but it's important parameter, as we will see of our problem, which is multiplied by the stream function. Okay, so if we look at the first two equations, x and z momentum, we can do, again, similar exercise. So we can start to solve each term. So du prime dt, again, will be minus ELC u prime, but u prime is equal to dz psi. So I can, of course, I cannot do nothing more with this one because it's, I mean, it's the unknown, it's what I'm looking. So I'm looking for what is the effect on the vertical of my perturbation, plus u bar du prime dx. So du prime dx again will be EL u prime, but u prime is again dx step c, dz, sorry, c, dz c, plus what we have, w prime, which is minus dx psi, which means, yes, here maybe there is a plus because there is a minus, so this is minus EL psi, and then we have du bar dz, which is equal to minus 1 over 0 dxp prime. Let me check that everything is correct. Okay, z momentum equation, dw prime dt. So we have still that w prime is a function of the Fourier-like. So we will have again minus EL C multiplied by w prime, which is minus dx c, which is again minus EL c, plus u bar dw dx, w prime dx, so again EL, and then minus EL c, and then I will have minus 1 over 0 the p prime dz, and then I can also here, I can substitute to rho prime the solution that I found before. Which I can also remove G and so I obtain two equations which are basically dependent on the variation in Z of psi, are dependent by my parameter, which is the shear actually, and then of course there is the pressure, and finally not just the variation in Z, but also the stream function itself. Okay, so as usually in these cases, I will apply cross derivation. So I will partially derivate the x momentum by z and the z momentum by x. Okay. In this way, the terms in the pressure, and then I will subtract one from the other. Okay. So we'll do all the operation in this, I will do all the operation in this, and then I subtract one to each other. When I subtract, of course, these two terms here will be removed and I will obtain just one equation. Okay, so when I do the z derivative, of course I act only on this, so I will have minus ELC okay, yes. Good. So what we can do is to put together this one and have u bar minus c dz c with minus il plus. Okay? So I put together, since I have the common term il dz dz c, I put together these two and I obtain this term here, and the same I can do it here. Okay? So I will have u bar minus c multiplied by el and minus el c. So making all the derivation and finally making the subtraction, we will obtain EL u bar minus c, second derivative of z with respect to z to c, minus EL c, second derivative of the basic flow, minus EL c L squared u bar minus c, which is equal to minus N squared u bar minus c here. Okay? So practically, z derivative of this, x derivative of this, subtraction of the two terms, important removement of the terms with respect to the P prime, to the perturbation pressure, and what we obtain is practically this one. Okay? So in here I can remove all the dependency of the wave number L, so it becomes EL, because it remains here as a dependency. And I can rewrite again u bar minus c dz squared c minus L squared c plus, I can put this on the left hand side, n squared u bar minus c minus this one multiplied by c, which is equal to 0. So this equation here that we have obtained is a very important equation, which actually rules the behavior of a wave-like perturbation within a stratified flow with a shear imposed. Okay? Because we have the perturbation stream function, psi, which is related to the velocity perturbation in the two directions. We have the shear velocity, we have the stratification, and we have the two terms, C and L, which actually governs the propagation of the wave along the x and in time. Okay? So if we consider this expression, and okay, very important, just to remember, this is called Taylor-Goldstein equation. So if we consider a limited system, as we did yesterday, so which on Z is constrained between two solid boundaries, one at Z equal to 0, one at Z equal to H. So we can say that W prime in 0 and W prime in H is equal to 0. So we cannot have any kind of penetration, of course, of the flow across the boundary. So if W prime is in 0 and in H is equal to 0, I can also say that minus the x psi in 0 and H must be 0. Okay? Which actually means that psi 0 and psi H are equal to 0. Okay? Because this must be valid for every x. Because from here I just can again make the derivation along x, and so I can neglect this, and what I obtain is that psi is always 0 on the solid boundary. Okay, so when we take this equation and this boundary condition, we have in our front an eigenvalue problem. Okay, so an eigenvalue problem which has psi as eigenfunction and c as eigenvalue. Okay, so in the most, this is, I think that Kushma said it, that is impossible to solve. So we are not interested to solve this, but we are interested to a little bit more investigate what is the meaning. So if we have an eigenvalue problem, in the most general case, our eigenfunction will be psi. But in the most general case, we will have also its complex conjugate. I mean, we are in the complex field, complex domain. So in the most general case, if I have psi, I must have also psi star. And therefore, if I have c as an eigenvalue, I must have also c star. Okay, so it's complex value, complex conjugate. So if c, which is the phase velocity of the perturbation, don't forget, is equal to a real part CR plus an imaginary part CI, and its counterpart is CR minus ECI. Okay, so I'm just making very simple hypothesis. I mean, it's not a hypothesis. Yeah, I mean, I can, of course, describe the C as its real and imaginary component, and then I go in the expression for my stream function, which is actually the same expression that we have in U prime, W prime, Rho prime, and P prime. And we go here and we have E, L, X minus C, R plus or minus I, C, I, T. And I can start to decompose this. I have EL X minus EL CR T. And then I have I and I, which becomes I squared, which becomes minus. So I have minus plus L CIT. Okay?
I don't understand what we are doing now.
We are trying to analyzing this equation.
So find a dispersion relation?
We won't find a dispersion relation. We will find a relationship, so we cannot solve it. We are going just to try to hypothesize which could be the condition that, will be related to the possible solution of this equation. The possible solution of this equation is this one. So we are not able to solve this, but we are making some consideration on the form, on the behavior of this one, okay? Considering the only thing that we can do is to make this mathematical hypothesis, just this, to consider that the phase velocity will have two, the real and the imaginary part in the most general case. And to understand that when we have, and this is the most important point, when we have the imaginary part, what we obtain here is a real exponential. So it's not, this is the oscillating part, and this is the real exponential. So this is the point that I want to consider and to highlight. When we have Ci, which is different from 0, we have that this term is positive and different from 0. Okay? So it means that my perturbation will grow in time or will be destroyed in time. Okay? In particular, if we consider only the not the complex conjugate, but the value of C, what we will obtain is exactly the plus sign. Okay? So it means that let's say the real part of the eigenvalue that we obtain will give rise to a perturbation that will grow in time. This is a signal of instability. Okay? So we can say that there will be at least one value, if we have one value of the imaginary part of our eigenvalue, which is different from 0, we will have that the perturbation will grow in time, and so will engulf all the system, and we will have something which, as you have seen yesterday from the video, will give rise to complete mixing. On the contrary, if Ci is equal to 0, I will keep the stable oscillation, okay, without any kind of increase of exponential increase in time. So,
about the Taylor-Goodstein equation, I thought when we were driving it, we said that we are not going to allow any second derivatives.
We cannot allow, sorry?
So we do not consider any second derivative.
Second derivative. We cannot consider any second. Why? No, you said, no. There are two different cases. One is second order. Second order. So think like U prime, W prime. So we are having second order terms. This is second order derivative. It's different. Okay? So it's something, and we cannot, moreover, we cannot, and this is also, I mean, this is not a prime. Okay? This is U bar. So we can consider this, and we can consider also this. Okay, so we can say that we have stability the flow is stable if and only if Ci is equal to 0. Okay? So as I said before, this equation is not possible to be solved. So Cushman proposes a couple of further analysis of this equation, which is derived by using integral constraints. And one of these is simply rewriting psi as the multiplication of the square of u bar minus c multiplied by phi. Okay? So I make a transformation within the Taylor-Gordon equation, and this will help me to find the final, let's say, results of this analysis of this equation. And just to substitute this expression here, 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 and here. Okay? So it means to make the second derivative of this and blah, blah, blah. Of course, also the boundary condition will be conserved. So if we have, when we do this equation, when we do this substitution, and we make all the calculation, and then with the equation that we obtain, we multiply, because now our equation is in phi, no more in psi, okay? We will multiply all the equation by its complex conjugate, okay, in order to have the square modulus of phi, okay? So this is the first operation. The second operation that we will do with this equation will be to integrate between 0 and h in z, okay? So take this. If you like, you can do it. It's possible. I did it some times ago. You just have to spend some time, but if you like, you can do it. And so substitute this to this. Recalculate all the derivative. Multiply the equation by its complex conjugate in order to find the square modulus, and then integrate between 0 and h, taking in account that you have this boundary condition. So the Taylor-Gordon equation transforms in another equation, which is this one. So we will have the integral of n squared minus 1 over 4 du bar dz squared multiplied by modulus square of phi divided by u bar minus c dz equal to integral 0h u bar minus c d phi dz square plus L square modulus square of phi dz plus 1/2 0h second derivative of u bar double square phi square dz. Okay, still it is not possible to solve. I mean, well, I don't know, but it's completely very difficult to solve this integral. But what we can do is, again, considering that C is equal to Ci plus ECI. And when we have an expression which have a real part and an imaginary part, you know that that expression, I mean, if we have two complex numbers, zeta1 equal to zeta2, okay? It's like we have here, okay? Because we have C, which is here, which have imaginary part and a real part, and C, which is here, okay? So this term here can be written like x1 plus y1 x2 plus y2. Okay? So the complex numbers are equal when I have the real part which is equal and the imaginary part which are separately equal. Okay? So to do this, I want to have the complex number c at the numerator. So what I will have is to rationalize or factorize this equation. So I will multiply all of this in order that here I will have at the denominator I will have a positive and real quantity, and I just keep the complex number at the numerator. So again, if we spend some time making some computation, we will be able to separate the real part by the imaginary part. Since we are interested to CI, because this is what we want to know, when, don't forget that the question, when is the shear critical in order to create instability? So we will going to analyze the imaginary part. So the imaginary part will be CI 0h n squared minus 1 over 4 du bar dz squared phi squared u bar minus c squared dz equal to minus CI 0h d phi dz squared plus n squared phi squared dz. Okay? So this is totally real, so it's not part of our position. This will have, of course, a real part and the imaginary part, and what we extract is just the imaginary part, and this is the same, okay? Voila, very, very good. So, have a look at these integrals. So we have CI and CI. We have a term here which has two parts. One, which is for sure positive. One that we don't know can be positive or negative, because at the moment we don't know. And another part here, which is positive. So I have that CI is multiplied by a number which can be positive or negative. Then I have a minus, and CI which is multiplied by a positive number. So this equation, it's an equation, so must be satisfied. If I have n squared, which is larger than 1/4 of du dz squared, what we will obtain? We will obtain that this term is positive, this is all positive, this is all positive, but this is negative. So the only possibility is that CI is equal to 0. Because otherwise we will have a positive number which is equal to a negative number, which is not sustainable, it's not possible, okay? So the only possibility when we have a flow which has a Brunt-Weisser frequency squared which is larger than 1/4 of the square of our shear flow, the only possibility is that CI is equal to 0, and so the flow is stable. So this is a very, very important result that we have obtained without solving, of course, precisely our equations in our problem, but actually it answers to the initial question, which is the limit, which is the critical limit that I will have create stability. The critical limit is until I have n squared larger than this term here, the flow is stable. The question is, okay, what happens if n squared is smaller than 1/4 du dz squared? So if n squared is smaller, it means that this term is negative, okay? And so I have negative multiplied by a positive, which is equal to a positive with a minus. So I can have, in principle, that Ci is different from 0. But I can also have that Ci is equal to 0, okay? Mathematically speaking, I can have both solutions. So for sure, I can say that this is a sufficient condition for stability, but this is a necessary condition for instability. So if I have n squared, which is larger than this number, I have stability. But I'm not sure that if I have n squared, which is smaller than this, I have instability, because the equation is not strictly saying that, okay? However, if we move from the theoretical side to the real side, we will say, and we will make observation, we will make measurement in different aspects. We will see that when we have a flow which is, when n squared is larger than this, we will have stability. And when we have a flow which is, when n squared is smaller than this, we have an instability, okay? So we can now use a new adimensional number, which is the Richardson number, which is nothing more than the ratio between the Brun-Weisel frequency and the square of the shear. And so we will say that when this is larger than 1/4, we have stability. When this is smaller than 1/4, we have instability. So the initial question, when we have the critical, where is the critical point to start our instability, is when the stratification will be such that the Brun-Weisel frequency will be smaller than 1/4 of the shear square, which actually has the same dimension of a frequency square. Okay, is a squared velocity divided by a square length. So Richardson number is extremely important and gave us the opportunity to answer to the question, even if the way we arrived where was not, let's say, strictly, didn't strictly follow a complete resolution of the Taylor-Goldstein equation, but in some sense we are satisfied, okay? Because this is exactly what we wanted to know, okay? If I have this problem here, I can hypothesize that I have the perturbation which has a certain dependency on Z in the vertical. But what I'm interested is, I will never go to measure the perturbation. Okay? I can say, okay, I have the perturbation, but what I know macroscopically is the Brun-Weisel and the shear flow. Okay? So if I have a shear flow which is, for example, let's say AZ, okay? So is increasing positively with A in the Z, and n squared, which is I don't know, beta, for example. So I can just, and these are numbers that I can measure. I can just say, okay, when beta is larger than 1/4 of A squared Z squared, I can have stability, okay, or instability. Okay. Of course, you can have, in the most general case, that Richardson number is a function of Z. Okay. Because if I say this, it means that I am having, that U bar has a parabolic behavior, okay? Because the derivative is still linear, okay? Of course, if I have a linear, I will have the Richardson number will be the same along the Z. But if I'm having this example, for example, as a case, I will have that in the most general case, the Richardson number will be dependent on Z. Okay, so actually, if we consider a simplification of our system and we recover our two-layer system, okay, so U1, U2, ρ2, ρ1, as we saw yesterday. So what we can say is that du bar dz can be like U1 minus U2 over H, if this is H, and n squared will be G ρ0 ρ2 minus ρ1 over H, okay? So I'm just rewriting the shear stress and the Brun-Weisser frequency in the case that we had yesterday, okay? So I can calculate the Richardson number. So what I have is G ρ0 ρ2 minus ρ1 over H minus 1 into over H. And so what I have is this is square. Okay. There's a shear, and so we can take 1 G H over ρ0. Okay. So when this is less than 1/4, we have instability. If you remember yesterday, we found less than 1. Okay, so it means that we have instability when the potential energy is smaller than the potential energy loss is smaller than the kinetic. The potential energy gain is smaller than the kinetic energy loss. Okay, so as soon as until the kinetic energy still is larger than potential energy, we are continuously creating instability, and so we are arriving to the complete mix. So the difference between the two numbers are related to the fact that the derivation of the Richardson number, of course, has started from a most general case. Okay? But still, the idea is still the same. Okay? So this means that even if we had defined the Richardson number just by analyzing the Taylor-Goldstein equation, so in some sense, neglecting any kind of relationship with the physical world, actually, Richardson number has also a physical meaning, of course, as the Rossby number, the Ekman number, and so on. And it's actually the ratio between, let's say, the stratification and the power of the vertical shear. Okay? So if the stratification is larger than 1/4 of the, let's say, power of the vertical shear, so the vertical shear, which brings kinetic energy, is able to erode, to destroy the stratification, is larger, so the stratification is strong enough to maintain the stability. If the stratification is smaller than 1/4 of the vertical shear, it means that stratification is weak enough, or the shear is strong enough to destroy the stratification and so create instability. So we want to know something a little bit more to conclude the lesson about our system, and we can try to analyze, so to come back again to our system and to consider one parcel which is oscillating, okay, traveling with this perturbation. So we can express W prime, which is our vertical velocity perturbation, as dA over dt plus u bar dA over dx, where A actually is our Z. Okay, so it's the vertical displacement. Okay, like H we said yesterday. Okay, in the case of the you can also use H as you like. Okay. So it means that I am a parsen and A is my vertical displacement, so which is traveling with the perturbation W prime and with the basic flow U bar. Okay, of course there is no more other terms here, because if I add also the advection over Z, I will have a second order again, because we have, this is still a perturbation, A is still a perturbation, so A will be also like same Fourier-like behavior. And so we have W prime plus the Z variation of A, which is a second order. Okay, so if we use this, so we have the variation in time of A, which means again ELC minus A, and U bar ELA, which is again U bar minus C multiplied by EL by A, which is W prime is still related to our psi, so we have again minus EL psi Z so we have this expression here, which is equal to this expression here, so we can neglect this and this, we can neglect this, and what we obtain is that minus C is U bar minus C A. Okay? So we have another integral constraint, which we can still include in the Taylor equation. And we again found an eigenvalue problem, so T the Z U bar minus C squared dA dZ. So before we had the integral constraint phi, which helped us to find the Richardson number relationship. Now we have the integral constant A plus n squared minus n squared U bar minus C squared, much smaller, and also the boundary condition. Okay, this is much easier. Again, we can do the same operation. So we will multiply by the complex conjugate. We will integrate between 0 and h, and finally we will. No, this is not doesn't need, because we always have everything on the numerator. Okay. So when we do this, and again we divide by the imaginary and real part. Don't just keep in account that we have U bar minus C to the square, which means U bar minus CR plus ECI squared, which is U bar minus CR minus ECI squared, which is U bar squared plus CR squared minus CI squared, and then I have all the double product, minus 2 U bar CR plus 2i CR CI and minus 2i U bar CI. Okay? So again, I can separate the imaginary from the real part, and here I have 1, 2, 3, 4 real terms and 2 imaginary terms. So what I obtain is minus 2ci 0h U bar minus CR multiplied by a factor P, capital P, dz, which is equal to 0. Where capital P, here, just as a reference, is a quantity which is positive and is the square derivative in z of a plus L square A square. Okay, so in some sense I have taken this part, the expression which comes after the treatment of the equation in A, and grouped all this part which are strictly positive in the factor P. Okay, so when we have stability, Ci is equal to 0. Good. Ci is equal to 0, no problem. But if we don't have stability, which means that Ci is different from 0, this term here must be satisfied only when U bar is equal to Ci. So we are again, we are not able to find the vertical behavior of our vertical displacement, AZ. Like before, we were not able to find psi z or u prime z or w prime z. But we are having an indication of the real part of the phase velocity of our perturbation, which actually must be equal to u bar. So it means that my perturbation will have CR, which will be between U bar min and U bar max. So in my case here, if I have, for example, shear like this, so U min will be 0, for example, and U max will be this value here, okay? So the perturbation actually is having a value, a real value, so this is meter per second, okay, which will be included, constrained between these two terms here. So I cannot have all the possible value for my phase velocity. Okay? I can have a value which is between, in the range of the value of the basic flow. So I'm having a basic flow U bar, okay? U bar Z, which has a gradient, which has a shear. So U bar will have its typical values, its typical form. My perturbation is actually traveling at the same velocity or with a velocity which is within the range of the basic flow. So it means that my perturbation is actually extracting energy from the basic flow, because it's taking the characteristic of velocity of the basic flow and it's bringing, when Ci is different from 0, to the instability. So the instability is growing, some says, within the basic flow. So if the basic flow has a perturbation, there is, within this perturbation, there is an instability, there is the possibility of the instability, which actually is traveling with the same velocity of the basic flow. This is exactly what happened when you have in the mid-latitude our planetary waves, which are perturbation of the geostrophic flow. And within the planetary wave, for some instability reason, there is the evolution of an instability, which at the end cause the cyclones, the baroclinic cyclones, which actually take most of the energy in their scale, which is the mesoscale, and so extract the energy from the basic flow, which is the planetary flow, and due to the baroclinic instability in that case, create a minimum of pressure at surface, and so characterize in some sense the weather at the mid-latitude. Okay. Okay. So if we so the energy is actually extracted from the basic flow, and the perturbation grows at the expense of the basic flow. If we look to the real part of this equation, we will have another, of course, another expression, which after some manipulation, which, of course, even Cushman said after some manipulation, so we don't know exactly. Okay, if you like, if you enjoy, you can do it. I did it in the past, but once is enough. So we obtain that CR minus U min plus U max over 2 squared plus CI squared is less or equal than U max U min 2 squared. Okay, so this is the final expression, exactly like this one more or less, that tells us that if we consider the complex field, complex plane, where we have real part on the x-axis and I part on the y-axis, what we obtain actually here is a further condition on the value of CR and CI. We obtain one here, we obtain another one here. So this is a circle, actually, if we put, it's like you have x and y here. So the circle we have center in CI equal to 0, and CR equal to U min U max divided by 2, which actually is the average, sort of average, of our U bar. So we are taking the maximum value of, like this. So the maximum value of, which is like this one, for example, okay? Maximum value of my basic flow, minimum value of my basic flow, take the average, and so I obtain this point here, which is U min plus U bar max divided by 2. And then I will have a circle which has a radius, this one, U max minus U min divided by 2. The semi-difference of the two extremes. Okay? This is nothing more, I mean, all before it was incredibly complicated, but this is quite easy. Okay? So, this means that any value of my phase velocity, so the phase velocity, don't forget, we are still looking at the perturbation, which is traveling at phase velocity c, which has a real part and an imaginary part. So the phase velocity c will live in a semicircle which start from Ci equal to 0. So here we have stability, okay? On this side we have Ci equal to 0. And it is limited by this term here. So Ci is maximum equal to the semi-difference. So it means that if you remember, the instability factor in my perturbation was related to LCI. So if I multiply this and I multiply this, I obtain practically a limit to my growing. So the instability doesn't grow infinite in an infinite way. Okay? So we are limited by instability rate, which is actually related to the basic flow. So this is called the Howard semi-circle theorem. Okay, don't forget this name because I can, for example, in the exam, I can write, please derive the general expression for the Howard semicircle. What is the Howard semicircle? So always put a label on your notes. Okay? So what we have learned today is that even if we can have a very complex flow to analyze, even if we can start from a very complex mathematical expression, which was the Taylor-Galson equation, we were able to somehow find some sort of general solution, general arguments, which at the end were able to help us to define a critical level when the perturbation become unstable, so create instability in the basic flow, and which are the characteristics of the perturbation, okay? Which, according to these 2 points, which, okay, this actually also takes in account this, because of course, this is U mean and this is U max, okay? So CR cannot be stay outside from the range of the basic flow. So the perturbation actually is traveling within, so can have a velocity which is larger of the maximum velocity of the basic flow or lower of the minimum velocity of the basic flow. And also the perturbation, the time, the exponential increase of our perturbation is limited to a certain level. Of course, we can have at the end, what we will have in reality will be a sort of damping term here, which of course otherwise it would be energy flowing everywhere, which is not possible, of course, which is related to the friction, actually, because you know, those of you, I think, no, you're from Guatemala, no? But you are experiencing tropical cyclones. So tropical cyclones actually are perfect, if you remember the thermodynamic laws, you remember the Carnot machine, so you have that, if you have a difference in temperature, you can actually create a sort of perpetuum motu, if you are able to keep the 2 boundaries at the fixed temperature, so there is a gradient. So actually, as soon as the tropical cyclones remains on the water, and the water is hot enough, because you must have like sea surface temperature which is larger than 28 degrees, 27, 26, okay. And you have the tropical cyclone started, they actually developed close to the West African coast, and then they move according to, following the major flow, the major tropical flow, and then they reach the Caribbean, and then they, so, but the same in the Pacific. But the problem is that when you, so the tropical cyclones are actually almost perfect thermodynamic machine. When they meet the land, of course, the effect of the friction is so strong in order to destroy the instability in that sense, and to actually damp the effect of the tropical cycles. Okay? So a similar damping effect, of course, acts also on that one, which more or less is related to the instability which creates the cyclones at the mid-latitudes. Okay? Okay.
Excuse me. I wanted to ask you one thing. I don't understand the relation between the phase velocity and the fact that the perturbations are extracting energy from the medium. Because generally we are referring the group velocity to energy.
Yeah. You're totally right. Yeah, we didn't talk about group velocity, we didn't talk about, but basically speaking, of course, within this system you will have a dispersion relationship. Okay, because if you have this kind of perturbation which is Fourier-like, you will have something which is related to, you will have in most general case, the frequency will be related to the wave number, okay? Because here we have just taken one single phase. In the most general case, we will have different L, and so we will have different C. And so if we have different C and different L, we can make, we have different waves, and we will have
the propagation of
exactly. And so the link between these things here and the fact that that Cushman say that you are extracting energy can be more strictly seen when you actually take the Reynolds average Navier-Stokes equation, and you do exactly the same thing, and what you have is an expression of the mean kinetic energy and of the turbulent kinetic energy. And the turbulent kinetic energy actually is related to perturbation like this. And when you have those two energy, you will have that there will be, so if you have like the mean kinetic energy equation and the turbulent kinetic energy equation, in these two equations there will be one common term which is, I have to remember, but something which is related to
the correlation times
something like this, okay? Where in one has minus and in one has plus. This means that this is exactly related to the perturbation and actually extract energy from here and put energy from here, okay? So it's not, I mean, mathematically it's not difficult. I mean, it takes some time. But I found when I did it as a PhD student, I enjoyed very much to do all the computation and to find actually this stuff. You can find, for example, a very nice book of turbulence, which is called the I don't remember, but okay, I will look, and it is written in, it is you can find it in the library, which explain very well this expression here. Okay, so actually this is a sort of enlargement of all this this topic, in order that at the end what you have is that the turbulent kinetic energy actually grows at the expense of the mean kinetic energy, which in our case means that the perturbation grows at the expense of the basic flow.
So if the phase velocity is equal to the mean flow, there is a greater turbulent flux or something.
Sorry, if
the phase velocity is equal to the mean flow?
Mm-hmm. To the mean flow, you mean? But the mean flow is most generally is a function of z.
Okay.
So we'll have minimum value and maximum value. Okay. When you say CR is equal to UZ, it means that CR will have a value equal to uz. We are not able to understand which value exactly.
Actually, there we're using the average theorem of integrals. Exists an average.
Yeah,
value
exactly, absolutely, exactly,
something like that.
exactly.